Okay, welcome to our first webinar of this year for the Pavement ME design. The topic today is reflective cracking. Next slide, please. I'm Clark Morrison with the North Carolina Department of Transportation and chairman of the Pavement ME design task force. Hari Nair of Virginia DOT is the co-chair. Our presenters today will be Harold Bonquintus and Wouter Brink of ARA. And please note that this presentation will be recorded and available for future viewing at the ME Design Resource website. That's me-design.com. Next slide, please. The Pavement ME Design Task Force provides oversight and guidance for the development, maintenance, and support of the AASHTOWare Pavement ME Design software program. The task force is guided by Ryan Fragapane, our AASHTO project manager. I mentioned myself and Hari Nair are the chair and co-chair. Also on the task force is Patrick Birrell with the Ohio DOT, Kumar Dave with Indiana DOT, Felix Doucette with the Quebec Ministry of Transportation, Dulce Feldman with California DOT, Ian Risch with Georgia DOT, Suzanne Chan is our liaison to the Transportation Association of Canada, and Tom Yu is our FHWA liaison. Next slide, please. Some housekeeping issues to start with. Phones and microphones are being muted, so please post your questions in the Q&A box. This can be accessed by clicking on the WebEx Q&A button. The presenters will answer all questions at the end of the webinar as time permits, and questions that are not answered because of time will be responded to separately. And with that, I'll turn it over to Harold and Wouter, and I believe they're going to start with a poll question.
Yes, thanks, Clark. It's going to work a little bit differently since WebEx changed a few things with how their events are set up. So our poll questions are going to be from an external link. So if everybody can go to the chat and or the Q&A, I'm going to post the link to poll question number 1. And that should show up for everybody. And hopefully everybody can link to it. I'll monitor the responses. Okay, so they are coming through. We have about 24 responses so far. If you are just joining, we added the poll question 1, or the poll 1 questions as a Google form link, which is posted in the chat window.
Wouter, will they be able to answer the questions toward the end and or during the presentation?
Yes, I have another poll set up for
Okay.
poll 2.
Okay. So it's been a little bit over almost 2 minutes. So if you would monitor that, I'll just go ahead and continue then with the webinar.
Sure. And the poll questions will, well, the link will be open the entire time, so they can answer at any time.
Okay. Okay, so welcome everyone for or morning or afternoon, depending on where you're at, to the, as Clark said, to the first webinar for this fiscal year 2022 of the AASHTOW Pavement ME webinars. For this webinar, we hope that the individuals or everyone attending does have prior experience with the Pavement ME software for rehabilitation design for both flexible and rigid pavements, or at least one, and also would have some experience with using deflection testing for, deflection testing relative to rehabilitation design using Pavement ME software. Our learning outcomes, there are 4 of them today. The first is to go over or describe the fracture mechanics based model included in the Pavement ME software for predicting reflection cracking in asphalt overlays. And that's asphalt overlays of both flexible and rigid pavements. Our second outcome is basically defining the importance of the load transfer efficiency for cracks in existing pavements and their impact or its impact on the prediction of reflection cracks. Our third learning outcome is basically using the Pavement ME software for predicting reflection cracks and asphalt overlays. And then the final outcome that's really tied to the third is simulating different reflection cracking mitigation strategies like interlayers, seal coats, and other non-structural layers in accordance with the Pavement ME software itself. So with that, this is the outline of the webinar for today. There's really 6 items. 1 through 4 will be kind of a summary. And then topic 5 will be where we spend about half the time on simulation of the mitigation layers for reflection cracking. And then we will have a summary, closing comments, and then questions and answer session at the end, like we typically do for each of the webinars itself. So we'll start with the history. Very briefly, webinar version 2.1 and earlier versions, the prediction of reflection cracks were simply based on a pure empirical regression equation, and that regression equation was only applicable to load-related or fatigue cracks. The reflection cracking fracture mechanics model was integrated in version 2.2 and is applicable to both load, fatigue, and non-load related cracks, transverse cracks of both flexible, semi-rigid, intact concrete slabs and fractured concrete slabs and or pavements.
Hey, Harold.
Yes.
Just a quick, could you go into presenter mode so it kind of takes up the whole screen?
Oh, thank you.
We were still in the reading view.
Thank you.
There we
go. Let me go through this and I'll get to where I was. And so thank you, Vooter. Also, Vooter, if you would, because I've had problems with my internet the past couple of weeks. If my sound starts to go or anything, please let me know.
That sounds good.
Okay, so the types of reflection cracks for all types of pavements and rehabilitation design. the Pavement ME software does consider fatigue and transverse cracks separately for all design strategies. As noted previously, version 2.1 was only applicable to reflective fatigue cracks. And the fracture mechanics based version added the non-load thermal or transverse reflection cracks that were included. As a reminder, the reflection cracking, transfer function, and/or models were integrated in Pavement ME from the product of NCHRP 141. Dr. Robert Litton was a principal investigator and did all of the work or guided all of the work in developing this fracture mechanics based reflection cracking procedure. All of the updates on reflection cracking are included in the 3rd edition of the MEPDG Manual of Practice itself. In addition to Dr. Litton, who with the Texas Transportation Institute was involved in the original NCHRP project and also assisted with answering questions and expanding on the neural networks for the reflection cracking models that were integrated in Pavement ME. More importantly, Halil Salam with Iowa State University completed all of the neural nets, the original ones, and then the expanded neural nets that are now included in the Pavement, or that were included in the Pavement ME software. I think in 2015 or version 2.1, and as well as later versions of the software. So now moving on, we want to now go through the mechanism and the designs. There basically are 3 types of mechanisms that are included. The first and more important is the differential vertical deflections across joints and cracks in asphalt and rigid pavements. These are traffic induced and they're basically shear related. The cracks initiate and propagate in shear itself. The second mechanism is thermal expansion and contraction of the joints and cracks in the asphalt and or rigid pavements. Obviously, that is thermal induced, and the crack initiates in tension, but propagates in tension and shear over time. The third mechanism is bending related, and that's where we get higher deflections in the overlay directly above the cracks in the existing pavement. Obviously, this is traffic induced, and the crack initiates in tension or flexural, and then propagates in tension and shear itself. Those 3 mechanisms are schematically illustrated in this slide. The 3 that we'll refer to are shear, thermal, and bending. And basically, when a wheel load goes across the location of a crack in the existing concrete or asphalt layer, there are differential deflections when the load goes across the crack. Those are related to shear in the asphalt overlay. There's also the bending as the load goes across the crack in the existing pavement, where we have increased tensile strains at the bottom of the asphalt overlay. And then the thermal, and that's simply the horizontal movement of the concrete base and or asphalt layer that causes tensile strains at the above the crack in the concrete and or asphalt base in the asphalt overlay itself. Now, to identify the most important of these 3 components, shear, bending, and thermal, which one is the most important, or are they all three significant? And this slide or this first graph shows the reflection fatigue cracks in each of the individual components shown at the bottom: shear, bending, and thermal, and their importance or their proportion of the total fatigue reflected cracks in terms of percent total lane area over a 10-year design life. And as you can see, the shear component, which is the black solid line, represents the majority of the damage resulting in a reflection crack. The bending and thermal component, the bending is the solid kind of orange line at the bottom, and the thermal component is the dashed black line at the bottom. They do provide some contribution, but it's minor compared to the contribution of shear. So shear contributes most of the fatigue reflection cracking prediction in most cases, or in the majority of the cases. This next slide shows the same thing, but for transverse cracks. And it's a summary showing or resulting in the same observation that we just made for fatigue. The shear, which is the solid black line, contributes most of the transverse reflective cracking prediction. The bending in the solid orange and the thermal component in the dashed black lines are minor compared to the contribution of shear as related to reflective transverse cracks. And that's true for most of the situations or the designs, the rehabilitations designs with using the Pavement ME software. Now, the different rehabilitation, types of rehabilitation that can be performed and that are applicable to reflection cracking are listed on this slide. There are semi-rigid pavements where there's asphalt layers over a cementitious or a cement stabilized layer. And reflection cracking does apply, and that's for a new semi-rigid pavement. We have asphalt overlays, flexible pavements, asphalt overlays of semi-rigid, asphalt overlays of intact jointed plain concrete, asphalt overlays of fractured jointed plain concrete pavements, and then asphalt overlays of CRCP. All of these reflection cracking would be applicable to all of these different rehabilitation strategies. ME does that are related, to rehabilitation, but are considered or assumed to be new flexible pavement designs relative to the MEPDG manual of practice. These two are asphalt overlays over a rubblized PCC slab and full depth reclamation of flexible pavements. Since these two strategies are simulated as new flexible pavement design, reflection cracks and reflection cracking prediction is basically a non-issue. The other flexible pavement rehabilitation techniques that do have application for reflection cracking and that we will cover today are hot in place recycling and then cold in place recycling. Obviously, if the cold in place recycling is consuming the entire asphalt layer that is being recycled in place, then that would be simulated also as a new flexible pavement design. If all or the majority of the existing asphalt layer is mixed in place or recycled in place, then that would be considered a new flexible pavement design. and reflection cracking would not be applicable. The different design strategies that are included in Pavement ME are listed in this slide. The first is simple asphalt overlays on an existing pavement surface. The surface is asphalt that can be milled or not milled. We can also have a simple asphalt overlay over a jointed plain concrete intact, and or an asphalt overlay over a CRCP. We can also have asphalt overlay design with chip seals or seal coats, as shown in the drop-down box from Pavement ME on the right. The third we can do is an asphalt overlay with an inner layer. And then two others that are not shown but can be simulated using Pavement ME, which we will cover, are asphalt overlays with a SAMI, a stress or strain absorbing membrane inner layer, and then an asphalt overlay with a crack relief layer. And we'll cover each of these conditions today in the webinar. So now we want to move to basically the inputs. What are some of the inputs for the different design strategies? And I'm going to go through these as you would see them when you're using Pavement ME. The first are the threshold values, and I just want to make a few statements about the threshold values, specifically related to reflection cracking, or as shown at the bottom of this slide in blue, AC total fatigue cracking, bottom up and reflective, and AC total transverse cracking, thermal and reflective cracking in feet per mile. Some agencies use a different threshold value between total fatigue cracking and reflective, as opposed to new bottom-up fatigue cracking, as shown on the third or fourth line down at 15%. It's generally recommended that the same threshold value be used for new AC bottom-up fatigue cracking and AC total fatigue cracking that would include new bottom-up cracks in the overlay and reflective fatigue cracks from the existing asphalt pavement itself. Those should have, or it's generally suggested, that the threshold values be the same. That is also true for transverse cracks, where the AC total transverse cracks, which includes new as well as reflective transverse crack from the existing asphalt layer, that threshold be the same as new AC thermal cracking developing at the surface of the asphalt layers. It's generally recommended that those be the same threshold values. For the semi-rigid pavements and or overlays of semi-rigid pavement, this shows the threshold values. And a little different here, where the total fatigue bottom up and reflective cracks should be the same as new fatigue bottom up cracks, should be either equal to or greater. Well, it should be the same for new bottom up fatigue cracks. The chemically stabilized layer, and that's shown by the orange box, where the cement treated base fatigue, that's threshold value is typically equal to or can be greater than the total bottom up fatigue cracking in the asphalt overlay. The transverse cracking would also be the same as new transverse cracks as shown on this slide. And the reason why it's generally suggested that the CTB fatigue in terms of fatigue fracture could be greater than the total of the bottom up fatigue is that it may take time for or it does take time for any fatigue cracks in the CTB layer to propagate through the asphalt overlay, so they may not always be observed once the cracking starts in the chemically stabilized layer. So in general, about 5% sometimes is generally suggested for the CTB fatigue layer. So in this condition, if we had 15% AC total fatigue cracking, as shown at the blue as a threshold value, then we could set the chemically stabilized layer to be about 20%, but that's up to the designer itself and or the agency for providing a suggested threshold value for the chemically stabilized layer relative to AC total fatigue cracking. Okay, now this includes some of the other inputs, and I'm going to go through these just showing what the software considers. The one on the left is asphalt overlay over a flexible pavement, or as shown on the pavement ME screen, AC over AC. There's generally three inputs related to reflective cracking. One is the mill thickness, and then the other two, or really three, are shown on the red box, and that is fatigue cracking and transverse cracking in terms of what exists on the existing surface, or what's there and can be recorded on the existing pavement. As shown in this example, we have 10% fatigue cracking, percent total lane area, that has a low severity. We have, as shown in the example on the left, 450 feet per mile, but those were classified as high severity. On the right, the input, we have a mill thickness of 2 inches. We have fatigue cracking of 14% total lane area of a low severity, and this is an AC over a semi-rigid pavement. And then the transverse cracking is about 800 feet per mile, and that's been classified as having a high crack severity. So those are entered, and the reason the severity level is entered, because this is for basically rehabilitation input level 2 for both AC over AC and AC over semi-rigid. The reason the severity level is entered is rehab input level 2 assumes that the crack severity is tied to the low transfer efficiency of both transverse and fatigue cracks. In other words, we wouldn't have any FWD deflection data to measure the low transfer efficiency. So in this case, the crack severity in terms of the pavement ME global values are tied directly to crack severity. This next now shows semi-rigid, and that's where we have an asphalt layer over a CTB or a cementitious stabilized base layer. Our three inputs for semi-rigid pavements, as shown in the red box from the pavement ME drop-down screen, that is the crack spacing, the transverse crack spacing, or the shrinkage crack spacing of the base layer, the CTB, which is shown in this example is 25 feet. The low transfer efficiency of the transverse shrinkage cracks, which is shown in this example, is 50%. And then also what will be the low transfer efficiency of the fatigue cracks that develop in the CTB or the chemically stabilized base from a load standpoint over time. And then this example, that's shown also as 50%. The 50% for the transverse and 50% for fatigue, those are the global default values. As I said previously, the low transfer efficiency of the chemically stabilized base can be measured with the FWD. The low transfer efficiency of the fatigue cracks, since they occur later, is typically considered or included as a calibration parameter. This next now, the inputs or threshold values for AC overlay of an intact PCC. It's basically the same or similar. Well, it's not similar to semi-rigid. Basically, we have the important point here is that as shown in blue in the drop-down screen, AC total transverse cracking, thermal and reflective should basically be the same as AC thermal cracking new, shown in above row of this drop-down screen. Those basically should be similar. And then the threshold for the JCP transverse cracking would also apply, and that's shown as 20% in this screenshot. This next is AC overlay of fractured Portland cement concrete slabs. Our value here shown in blue, the line item shown in blue is AC total transverse cracking, which is thermal plus reflective. And that also should be, it is suggested to be the same as AC thermal cracking new, shown in one of the above rows in this slide. Basically, they should be the same, or it's generally suggested that the threshold values be the same. The next is the inputs for the AC over fractured jointed plain concrete pavement. There's basically two for characterizing that PC fractured slab, and that's the crack spacing, which is normally 3 feet. That's the default, but that value can vary from about 2 to 5. And then the low transfer efficiency of those fractures itself. 50% is shown in the screen, and that is the default value. That's the global default value. Next is the AC overlay of the CRCP pavement. And again, it's recommended that the AC shown in blue, AC total transverse cracking, thermal and reflective, that really should be the same as AC thermal cracking in the above, shown in the above line item. It's not shown to be the same here. That just forgot to change it. It's generally, they should be the same threshold values. And then also the CRCP punch out shown in the lower row of the drop-down screen. Now, moving on from the inputs, we want to briefly note the calibration coefficients and just mention and provide a couple of comments about the calibration coefficients themselves. The calibration coefficients, these were derived using the LTPP sites and a few other non-LTPP sites where data existed, and it was recommended for use within the NCHRP study 141, but the majority of them came from LTPP. And the majority of those sites were basically overlays with and without milling. A large majority of the LTPP sites for the rehabilitation, the calibration of reflection cracking, came from the LTPP SBS 5 and SBS 6. And had to do with the asphalt overlays of flexible pavements, SBS 5, and asphalt overlays of concrete pavements, both intact slabs and fractured slab, as a part of the SPS 6 LTPP program. It's important, however, we wanted to make sure we made this note. It's important that an agency and or a user, designer, verify the predictions using agency-specific data, especially using mitigation strategies. The asphalt overlays with and without milling, kind of a basic simplistic overlay. There are many of those in the calibration database that was used. There's much fewer test sections where a seal coat was used between the overlay and existing pavement, whether an interlayer, even fewer interlayers between the asphalt overlay and the existing pavement, and then almost zero crack relief layers and very few like SAMI layers were included in the LTPP program. So it's important that the use of these reflection cracking prediction transfer functions and models be kind of verified using agency-specific data. And I'll get into that a little bit later in the simulations. Okay, this just shows an example of the screen drop-down box and the reflection or the rehabilitation calibration settings. This is specifically the calibration coefficients for AC over flexible pavements. I know the text is fairly small. The importance of this that I want to make is there is a group for the calibration coefficients for fatigue cracks, bottom-up fatigue cracks, and then a separate set calibration coefficients for transverse cracks in the existing pavement. With those, there are a set of what we call the K1, K2, K3 for both fatigue and transverse, as shown in the screen. And then there's a C1, C2, C3 that are the calibration coefficients specifically for the K1, K2, K3. C4 and C5 for both fatigue and transverse are the coefficients specifically in the transfer function. And again, we'll cover these a little bit later in the webinar when we talk about simulation at the end of the simulation of different reflection cracking mitigation strategies. But these were derived from the majority of the LTPP sites. And K1 is the bending stress component. K2 is the shear stress component. And K3 is the thermal stress component that we showed earlier in terms of the contributions of each of these components to the prediction of reflection cracking. And as a reminder, K2, the shear component, is the most important for the majority of the rehabilitation strategies and designs that a designer is going to encounter or use. This now shows the calibration coefficient screens of AC over fractured jointed plain concrete and or CRCP. Some of these only have transverse crack calibration coefficients because fatigue cracks in the asphalt overlay, bottom-up fatigue cracks are assumed not to occur. That does not mean top-down fatigue cracks do not occur. They do occur, and they are predicted in the Pavement ME software for these different rehabilitation design strategies, but those are not reflection cracks. The calibration coefficients for fatigue and transverse are only for bottom-up fatigue in the existing AC layer and or transverse cracks in the existing AC layer itself. Given that, then I've one observation we wanted to make, because a lot of these calibration sites were from the long-term pavement performance program. In terms of the seal coats, and to some degree with the inner layers, they do not result in a significant difference in predicting reflection cracking in terms of asphalt overlays over flexible pavements. The reason for that we'll get in a little later, but all of the, or majority of the sites, on the average, the seal coats and the inner layers made little impact on the predicted fatigue as well as transverse cracks on these sections that were used for calibration. Thus, it is important to verify, because that is not the case with some agencies where they have found and have verified that there is a contribution, especially for the inner layers, using some of the inner layers, as well as seal coats on delaying, not preventing, but delaying reflection cracks. And it's important to verify the predictions using agency-specific data. The other reason is many of these non-structural layers, like seal coats, inner layers, and others, are highly specification dependent. And so in some cases, like in Arizona, where inner layers are used quite successfully, they would have a different set of calibration coefficients on using some of their rubber asphalt inner layers, as opposed to just a straight asphalt overlay. The factors would be different. So now let's move to the simulation of reflection cracking mitigation strategies. This is where we'll spend probably about most of our time, or an additional 30 minutes or so of this time. And so we want to kind of go over the simulation of the reflection cracking mitigation strategies. We also want to look at what are some of the high impact input variables for whether we have an asphalt overlay of a flexible or rigid pavement. And we want to then go over how we simulate not only the strategies that are directly included in the Pavement ME software, but others that can be simulated, like hot in place recycling, cold in place recycling, the thicker crack relief layers, chip seals, seal coats, a non-structural inner layer, stress absorbing membrane. And then we want to spend a little time on material specific coefficients. So first, what are some of the high impact that have a large impact on the prediction of reflection cracking through the Pavement ME software? Obviously, one of the very important factors is the asphalt overlay thickness. It has a huge impact. And this graph or figure shows the reflection fatigue cracks for different overlay thicknesses. The solid line is a 4-inch asphalt overlay. The short dashed line is a 2-inch overlay, and the longer dashed line at the bottom is a 6-inch overlay. And you can see for fatigue cracks, overlay thickness, which we would expect, is very significant in delaying the occurrence of the fatigue cracks, and that's bottom-up fatigue cracks from the existing asphalt layer. This next graph now shows, again, the impact of asphalt overlay thickness, but for transverse cracks. And we see basically the same thing. If we the transverse cracks, therefore a 4-inch overlay, 2-inch overlay, and a 6-inch overlay. The 2-inch overlay is the short dashed line, and you can see they occur very quickly, and once they start to occur, they propagate very rapidly. The 4-inch, which is the solid black line, it takes longer for those cracks to propagate, about an additional 2 years for the cracks that are there in the existing flexible pavement. And then it takes, they don't start to occur, or we don't start to see them at the surface until a longer period of time, obviously. The 6-inch asphalt overlay is the longer dashed line, and that shows that basically it prevents the, within a period of 10 years, for only 10 years, prevents any significant reflection of the existing transverse cracks from the existing flexible pavement through a 6-inch asphalt overlay. The overlay thickness, very important for fatigue and transverse reflective cracks. Another very important parameter that we typically have ignored in the past is the load transfer efficiency. As I mentioned earlier, load transfer efficiency is tied to crack severity, at least from a global standpoint or global calibration, because load transfer efficiency was not measured within the LTPP program on flexible pavements, and that's the load transfer efficiency across transverse joint or cracks in the flexible pavement as shown in the photo on this slide. The graph on the right, that shows the total fatigue cracks, bottom-up fatigue cracking. The red line, or the red cross-hatched line, that represents high severity. The open blue circles represent a medium fatigue crack severity, and the green plus line on the bottom shows the low severity fatigue, bottom-up fatigue cracks. And as you can see, the crack severity and or crack low transfer efficiency is extremely important. The bottom graph shows the same thing, but for transverse reflective cracks. The red cross is high severity transverse cracks. The blue circle, medium severity transverse cracks, and the cross or the plus green line is for low transverse crack severity in terms of predicted transverse reflection cracks from the existing pavement. And again, for 10 years. So crack severity for both fatigue and transverse cracks in the existing pavement are extremely important in terms of when those cracks are going to reflect through the overlay. This now shows another example. The example on the top is no milling. The example on the bottom, or the graph on the bottom, is 1-inch mill. And this is for reflective fatigue cracks or reflective bottom-up fatigue cracks. Low transfer is important, and really milling only has a minor impact. The deeper mills, obviously going from 1-inch, 2-inch, 3-inch, depending on the thickness of the existing asphalt layers, the deeper the mills do result in more cracking. Or I think that the deeper mill should be less cracking. That's an error in this slide, I'll have to correct. The deeper mills should result in less cracking. Okay, this now shows the reflection cracking for transverse cracking. Again, low transfer efficiency is important. The solid black line on the top is for low crack severity transverse. The longer dashed line is for a medium severity crack transverse. The short dashed line is for high severity. The graph on the bottom is the same thing, but for only low and medium crack severity with a 1-inch mill. And the 1-inch mill, or the mills, basically the milling depth basically has a minimum impact on the predicted transverse cracks. Now, the simulation, move now into the simulation of different mitigation strategies. We'll first do some examples on no milling but with milling. We'll have without milling, we can have longitudinal cracks in the wheel path. And then the photo on the right shows we have an existing flexible pavements with transverse cracks with milling and then an overlay. Asphalt overlay layers for both existing pavements that are not milled versus those where milling is included is basically the same as for like a new asphalt layer. The only difference is simulating the existing pavement or characterizing the existing pavement. And so this is the, I went backwards, sorry. So this now shows the milling depth simulation. And I want to make this, or we want to make this statement again. We've noted it in memos. It's noted in the MEPDG Manual of Practice. But we want to make sure there's a clear understanding of what the thicknesses are entered in the Pavement ME software for a rehabilitation overlay design strategy of an existing flexible pavement. So we have an average thickness of cores of 5.5 inches for a design segment. That's the average thickness of the cores, 5.5 inches. We're then going to decide where we're going to mill the upper 2 inches. So we're removing the top 2 inches due to milling. So what gets entered into Pavement ME for rehabilitation level 1 or 2, we have, as shown in the middle box, we have a mill thickness of 2 inches. And then shown in the box in the bottom, we have the thickness of the existing layer of 3.5 inches. So the thickness of the existing asphalt layers is the average thickness recovered from cores minus the mill depth. So 5.5 minus 2, 3.5 inches. And that what gets entered into Pavement ME for the existing asphalt layers. Kind of focusing on the middle block, you can see we have our fatigue cracking of a low severity, but the amount of cracking is not entered because this is rehabilitation input level 1, and we're having the program estimate the amount of fatigue cracking. Transverse cracking is from the distress surveys, 400 feet per mile, and those were rated as a low severity. And both of those get entered into Pavement ME. Okay, so the damage, so let me go back. So how do we, if we're doing a mill and overlay, how do we determine if we're doing rehab input level 2, how do we decide on the amount of fatigue cracks that are remaining in the existing pavement? So damage is typically defined by the amount of cracking on the surface or back calculated using elastic layer theory for rehab input level 1. Those cracks are assumed at the surface or bottom up fatigue cracks if we do not have cores or FWD testing. So since they're assumed to be bottom-up cracks, any cracks we see at the surface, even though we're milling 1, 2, or 3 inches, that same amount of cracks, since they're bottom up from the bottom to the surface, that will exist regardless of the amount of milling depth for a specific design strategy. If we don't have cores, then we don't have FWD testing to evaluate crack depth or to look at cracking at the surface with different potential mill depths. So that is one suggestion, that if we're doing rehab input level 2, the cracks at the surface, if we're doing milling, those would also be entered for the amount of fatigue cracking for rehab input level 2. So now, milling and no milling. We have 2 examples that I've shown here from an example. We have a mill depth of 0 and then a mill depth of 2.5 inches. We have an existing pavement layer from cores, the first one would be 7.5 inches. That's a mill depth of 0. We're going to mill 0, and then we're going to simply place an overlay of 2 inches. The second example, we're going to mill 2.5 inches. So our existing asphalt and pavement ME is 7.5 minus 2.5. That's 5. Our replaced milled layer is 2.5 inches. And then above that, we're going to put 1.5 inch an overlay, dense graded overlay. So the graphs at the surface show the predicted reflection cracks on the left for fatigue cracking and the prediction of transverse fatigue cracks on the right. So if you're looking at the graph on the left, we have a mill depth of 2 inches on the black solid line, where those cracks are going to propagate fairly rapidly. And then by milling that, remove and replace, that's the dashed line where we're putting on only 1.5 inches more asphalt, but the total new asphalt is basically 4 inches. That's the replaced mill depth plus the overlay thickness above the mill material that is replaced. And so that shows the dashed black line shows the predicted fatigue cracks measured over 20 years. The graph on the right shows the same thing, but for transverse reflection cracks. So the 4-inch overlay in this case didn't provide a significant delay in those transverse cracks that existed in the existing pavement. Okay, now let's move to hot in place recycling. So the question, this is an option that's used, and the question is, will the hot in place recycling remove all surface cracks, but what about the existing damage? Rehab level 1 is what's preferred or suggested, as noted previously, because we'll use back calculated elastic modulus to determine the amount of damage in the existing asphalt that remains, and or our assumption that the cracking we see at the surface, if we do not have cores, then we assume all of those cracks have propagated from the bottom to the surface. So what we see on the surface would be entered for rehab 2, even for a hot in place recycling, the amount of bottom up cracking prior to overlay, after the hot in place recycled material is completed. Rehab level 2s use the condition survey and cores to estimate area of bottom up cracks and damage that's not recycled. Kind of just what I previously said. Okay, so this is our simulation. So rehab input level 1. This is we're milling 1.5 inches, as shown in the middle box for rehab level 1 is suggested. So the fatigue cracking is blank, the amount, because that's being determined by the program from the back calculated elastic layer moduli to define damage. The cracking is believed to be a low severity from the surface observations. Transverse cracking, we have 400 feet per mile that we see at the surface. prior to the hot in place recycling, and those are of a low severity. For rehab input level 1, I'll come back to this. As shown in the drop-down box on the right in blue, the back calculated average elastic layer moduli for the existing asphalt layer is 620,000 PSI at a frequency of 30 Hertz and at a average mid-depth temperature of 85 degrees Fahrenheit. A rehab input level 2 can be an option. If we do not have, if there's minimal cracking at the surface and we do not have FWD testing available, we have to, what is our amount that we're going to enter? And so for rehab level 2, I entered 1%, and I did that for a specific reason that I'll show in just a minute, low severity. But the transverse cracking is the same as 400 feet per mile, and we have mill thickness of level 2. The rehab input level 2, the fatigue cracking amount is decided on by the designer. That's a decision the designer has to make. As noted previously, it would be a suggested value that whatever fatigue, bottom fatigue cracking, wheel path cracking we see at the surface, if we do not have cores to confirm that that's top down and or bottom up, and we don't have deflection testing, then we would enter the amount of fatigue cracking based on the amount of cracking observed at the surface of the pavement prior to hot in place recycling strategy. So this now shows the difference. For rehab input level 1, in our example, I show a black line, that's for rehab input level 2, and this is for total bottom-up fatigue cracking in the top graph. And the dashed line that's for the rehab input level 2, or should be for rehab input level 2. And that, the dashed line, excuse me, the dashed line is rehab input level 1. So showing now the bottom graph, this is for the total length of transverse cracking. And so the assumption for transverse cracking is transverse cracking extend through the entire asphalt layer. So our assumption, I remember from the previous slide, originally I assumed, as shown for rehab input level 2, the lower box, we assumed only 1% fatigue cracking. And that would be that there would be no fatigue cracks on the surface. The upper rehab box at rehab input level 1 predicted the amount of fatigue cracks. So there's a big difference. And the big difference is the estimated damage. So it is suggested that doing rehab input level 2 for hot in place recycling, as well as other options, that for bottom up fatigue cracks, if we don't have cores to confirm whether there's bottom up or top down or FWD testing, that we just assume that any cracks in the wheel path observed is assumed to be all bottom up cracking. And that would reduce any potential discrepancies between rehab input level 2 and rehab input level 1. Would help reduce them. And in this example, I should have mentioned our hot in place recycling was 1.5 inches. Then we had an overlay of 2 inches. And then our existing asphalt layer below the HIR, hot in place recycled layers, was 6 inches. Now let's move on to a cold in place recycling example. And this is similar to hot in place recycled. We need to estimate cracks and damage remaining below our cold in place recycling layer, assuming we're not doing doing cold in place recycling of the entire asphalt layer. It's only a portion of the asphalt layer that exists. And we have rehab input level 1, which is preferred or suggested, and rehab input level 2. Rehab input level 1, just like our previous example, is going to use back calculated elastic moduli to determine amount of damage in the existing asphalt layer that remains. Rehab input level 2, we used a condition survey and cores to estimate the area of bottom-up cracking that's not recycled. Again, the same thing would be suggested where if we're just doing rehab input level 2, any cracking that's seen on the surface and the wheel path, we assume that's bottom-up cracking. And so that would go through the entire asphalt layer. And so that's the amount of fatigue cracking in the existing surface, bottom-up cracking, we would include in pavement ME. If we have cores and we know most of the cracking is top-down cracking at the surface, then that would not be the case. This now shows the rehab input level 1. We have an overlay of 2 inches. We're doing a cold in place recycling of 4 inches. And so our existing asphalt layer that remains is going to be 5 inches. So rehab input level 2, fatigue cracking amount is decided again by the designer. The designer makes that decision. This now shows the importance of the existing layer, the condition of the existing layers. And we included these just to show if we have a good intact or good asphalt layer versus a relatively poor condition asphalt layer, what impact does that make on reflection cracks? And so what we've shown here is an elastic average back calculated layer modulus of 580,000. This is for total bottom up fatigue cracking. And you can see we have about 20% cracks, bottom up cracks that are going to reflect through over a 20-year design. And so that's about 580 KSI. Here we have what would be considered a very good existing asphalt material, would have little damage in the existing layer. And so our back calculated layer modulus is 750,000 PSI. And you can see that no total bottom up fatigue cracks are going to propagate to the surface in that overlay. That 2-inch overlay with the cold in place recycled layer of 4 inches. If we have, however, 350,000 PSI for the existing layer, that indicates a lot of damage. And so we're going to have nearly 50% bottom up fatigue cracks occur at the surface of the overlay, and bottom up fatigue cracks through the overlay over a 20-year design life. So what that says is we need to do something more severe than a 4-inch cold in place recycling for this condition, either a thicker overlay and or a full depth reclamation, or use some other reflection cracking mitigation strategy when we have very poor underlying conditions of the existing asphalt layer. Okay, so now let's look at a crack relief layer. We're going to simulate a crack relief layer. So this is an overlay of 2 inches. We're going to use a crack relief layer of 4 inches and our existing asphalt layer of 5 inches. So we have an existing layer where if we have, let's say, 8 to 9 inches of an existing layer, we're going to remove to keep the final grade similar. We're going to remove the upper 4 inches and we're going then and replace a crack relief layer and then put a 2-inch overlay on it. And what I've shown here, this is the total bottom-up fatigue cracks predicted in the asphalt 2-inch overlay over 20 years. And you can see almost none of the cracks, or less than 4% of fatigue cracks are going to reflect. The solid black line is for the existing back calculated modulus of 580,000 PSI. And the short dashed line is the condition where we have 350,000 PSI back calculated elastic layer moduli for the existing asphalt layer. So the solid black line, it's a reasonable condition, has some damage. The short dash line would be, there would be a lot of damage in that existing layer. But this crack relief layer under this condition basically delayed those cracks from reflecting through the surface for both conditions over 20 years. This is another example comparing now just the crack relief layer strategy to the cold in place recycling strategy. The short dashed line is the 350,000 PSI of the existing layer, asphalt layer. The solid dash line in both graphs are the 580,000 PSI. So the condition of the existing pavement can make a big difference. The type of rehabilitation or reflection cracking mitigation strategy can also have a big impact, as shown in these two graphs. And the overlay design or the rehabilitation design strategies, the upper one is using the crack relief layer of 4 inches and an overlay of 2. And then the lower is using a cold in place recycling of 4. And in this case, we only have 5 inches remaining of the existing pavement layer and a 2-inch overlay. So the condition of the existing pavement, as well as the the reflection cracking mitigation strategy, can make a big difference in our rehabilitation design. They're both important. Again, looking at crack relief layer above a fractured Portland cement concrete. So we're using the same reflective crack mitigation strategy, but this is for a crack and seat or fractured PCC slabs, as opposed to or in comparison to using a leveling course and dense graded overlay itself. So I've shown the inputs here. We have a crack spacing fractured of 3 inches, or not 3 feet. That's the crack spacing in the PCC for the fractured slabs. And then we have the low transfer efficiency, in this case, of 65%. An elastic modulus of the PCC above the cracks of being basically 2 million PSI. And so the table at the bottom shows we have slab thickness of 10 inches. In one case, we're going to put in a 3-inch crack relief layer asphalt. We're then we won't have a leveling course, and we'll have a 2.5-inch overlay. The comparison will be not using a crack relief layer. We'll have a 1.5-inch leveling course, and then a 4-inch asphalt overlay. So basically 5.5 inches of new asphalt mix for both cases. The 3-inch crack relief layer plus the 2.5 overlay, 5.5, and then the leveling course of 1.5 and an asphalt overlay of 4 is 5.5. So now this shows the comparisons of these two strategies. The graph on the left is bottom-up fatigue cracks. The dashed line is basically the crack relief layer. The solid line is the leveling course, and using the leveling layer with dense graded materials, no crack relief layer. The graph on the right shows the predicted transverse reflection cracking. The solid line is the dense graded material. The dashed line is the strategy using a crack relief layer. So the question becomes, what happened to the graph on the left, bottom up fatigue cracks, where we show a lot more bottom up fatigue cracks than in using the crack relief layer? The reason for that is the crack relief layer has high air voids and low asphalt content. And used in this example, I think the example was like 20% air voids and only about 5% asphalt effective by volume. And so fatigue is going to play a role, significant role, because those typical layers have very low resistance to fatigue strength resistance, or they're susceptible to fatigue cracking. So the designer basically is going to have to make a decision now on what is basically used in terms of simulating these crack relief layers, very similar to the drainage layers of asphalt, permeable asphalt treated drainage layers below asphalt layers. The same condition applies here, or the same outcome a designer would see. And so in accordance with the Pavement ME Manual of Practice, the crack relief layer is simulated as a very high quality aggregate base layer. And that's one way to try to simulate that in terms of an overlay design to get around this issue. Okay. So the next would be now moving into chip seals and seal coats. This is an option as shown in the drop-down box and the box to the left of this slide, on this slide. And this is where we're using a chip seal or a seal coat above the existing asphalt layer that remains if we're doing milling, and then placing a dense graded asphalt overlay. And this is an option directly considered or included in the Pavement ME software. So doing that, the graph on the top right, this is the amount of bottom-up fatigue reflection cracks. The graph on the bottom is transverse reflection cracks. And so on the graph on the top, the short dashed line is for traffic of about very low lower traffic, trucks of about 400 per day. The solid line is for double that, 800 trucks per day. And so you can see trucks do make a significant difference. And that's true for both shown in the top graph for fatigue reflection cracking, as well as in the bottom graph, transverse reflection cracking. And so there is the lower truck traffic, it requires there is a delay, as we would expect, and then there is a longer time to propagate those cracks, both transverse and fatigue cracks, over a 20-year design. So truck traffic is important, as well as the thickness of the overlay. The one thing I'm going to remind here, everyone, that I mentioned earlier, is that the predicted fatigue and predicted transverse cracks, where we have AC over an asphalt overlay with seal coats, the predicted amount would be very similar if we just had an asphalt overlay over an existing flexible pavement, kind of with and without a seal coat. There's not a big difference in the predicted cracking between those reflection cracking mitigation strategies. The same is true for interlayers. As for the reasons I gave near the beginning of the webinar. So the top graph shows the same thing for fatigue, bottom-up fatigue reflective cracks. The graph on the bottom shows transverse reflection cracks. The solid line for both cases are truck traffic of 1,800 per day. The short dash line is 800 trucks per day. So again, trucks are important, as well as the asphalt overlay thickness is important. With and without seal coats, with and without the inner layers. And again, for the inner layers, there's a little bit greater impact for reflection cracking mitigation, or let's say delay. That's not going to prevent the cracks, but it'll delay them a very small, short time period, more than for the seal coats, based on the calibration data that was used from LTPP. This now shows the SAMI layers, or the stress absorbing, strain absorbing membrane inner layers. This is simulated where we have a thicker SAMI that's about an inch, as shown in extracted from Pavement ME on the screenshot. We have air voids because they're very high, like a polymer modified of 3%, and effective binder content of like 13%, and a lower density. Two examples where we have an existing asphalt thickness from cores of 7.5. We're going to have both a milling depth of an inch on the existing pavement, and then in one case, we're going to put a SAMI layer of an inch. We're going to have asphalt overlay of 3. In another case, we're not going to use the SAMI and have a 4-inch asphalt overlay. This shows the result for fatigue cracking. And as you can see, the short dash line, that's the predicted bottom-up fatigue cracks without the SAMI. The solid black line is the predicted bottom-up fatigue cracks with a SAMI, with the 1-inch SAMI. So the overall thickness, overlay thickness, is about the same, but we have predict less bottom-up fatigue cracks for the condition or comparison with the SAMI included in our simulation. This shows the same thing, but with total for transverse reflection crack. Same observation, there's a slight delay, a shorter delay though, for transverse cracking with the SAMI on the solid black line, opposed to without the SAMI, the short dashed line. The solid dashed line has the SAMI. The short dashed line does not have the SAMI. So now let's look at the different strategies, because I want to come back to these specialized mitigation strategies. This would be the SAMI layers, the inner layers, and other types of proprietary material that were not included, or if they were, there were only a few sites included within the calibration database to develop the global calibration coefficients that I showed near the beginning of this webinar. So we want to mention what are the important calibration coefficients and what kind of impact they have if we took some of the sites in LTP and use those sites that represent that don't represent, let's say, any kind of defect, or represent those sites from specific agencies that routinely use these strategies. And so these two graphs are going to show this first one shows bottom-up fatigue reflection cracks, and the solid line is the global calibration coefficients. That's what's in Pavement ME, and this is for bottom-up bottom-up fatigue reflection cracks. The y-axis, I guess I got to be more careful. It shows transverse cracks, but this is total percent lane area. So this should be bottom-up fatigue cracks over a 20-year design life. The short dashed line are the two major coefficients that were used in limited conditions or for specific agencies in simulating their specific typical reflection cracking mitigation strategy or delay strategies. And so the C2 global value is a 1.66, and the C2 for the material calibration coefficient is 1.2. The C5 for the global calibration coefficient is 7.02, and the C5 for the material agency specific calibration coefficient is a -8. So it's a -7.02 compared to a -8. And you can see that there is still a substantial delay, but eventually the amount of bottom-up fatigue cracks are going to equal basically the two for long design lives through pavement ME based on these different calibration coefficients. But if we were using a 5% total fatigue cracks, the global would end in about 12 years. That's the solid line, whereas the material specific would go to about 16 years or so for this one example. Now going to the same thing, but looking at transverse reflection cracks. And the global calibration coefficients are the same one, C2 and C5. The C2 for the global, the solid black line, is 25.7. The C2 for the dashed black line is 13, and that's the material specific calibration coefficient. The C5 global value is -72.4. That's in the Pavement ME software. The material specific calibration coefficient is a -115. And you can see there is a delay, predominantly of a delay of about 4 to 5 years between the two for transverse reflection cracks. Now, summaries and takeaways. The shear, this is just doing a quick summary and takeaway. The shear component of the reflection cracking mechanism is the most important one. Pavement ME predicts the amount and occurrence of bottom-up fatigue cracks and transverse reflection cracks for most of the reflection cracking delay strategies or design strategies. Reflection cracking calibration coefficients derived using asphalt overlays with and without milling. In other words, they were derived, majority of them, for the asphalt overlays that had both with and without milling. Much fewer sections were used for the other reflection cracking mitigation strategies. So those other strategies in using those calibration coefficients, they really should be checked and verified by individual agencies, that especially those that on a routine basis use these other mitigation strategies. The key inputs that have a significant impact on reflection cracking are asphalt overlay thickness, low transfer efficiency, that have to do with both fatigue and transverse reflection cracking, the amount of fatigue cracking and or damage in the existing asphalt layer is very important, and traffic is very important or has a significant impact. The important reflection cracking calibration coefficients to be considered are the C2 shear calibration coefficient, or K2, So C2 is the calibration coefficient for K2, stated differently. C4 as part of the transfer function, and that basically changes the magnitude of cracking at any point in time relative to the global C4. And C5 basically changes the rate of cracking over time. So C4 basically extends at a magnitude, kind of delays the cracking. C5 in the transfer function changes the rate of cracking. So the delay would be rate dependent. And so measuring low transfer efficiency at transverse cracks and joints does have a significant impact on transverse reflection cracking. The low transfer efficiency of bottom-up fatigue cracking is also important, also has a significant impact, but that is typically a calibrated parameter. And then on 8, kind of wrap it up, suggestions for future enhancements and considerations should be submitted to the help desk, the AASHTOWare site, and or the task force, especially those that might be related to reflection cracking as the purpose of this webinar. So with that, Wouter, if you would do the 3 final poll questions, and then we'll open it up to questions and answers for those that haven't been already answered.
Sure. We haven't answered too many. There's basically 2 or 3 questions that we'll answer at the end. But for the poll questions, I am entering the link to the Google Forms now. So if everybody could navigate to your chat and select the link that I just provided, it should take you to those poll questions. And there's 3 questions. The first one is, have you calibrated the reflection cracking transfer functions? Second is, if reflection cracking was calibrated, was there a change in the global coefficients? And then the third is, the webinar was useful for doing rehabilitation design. That is just for reference, so you kind of to see if there's 3 questions that that you're in the correct poll. I'm seeing responses, so I think most people are able to access it. We're about 30 responses, Harold, out of the 41 that remain.
Okay.
Do a quick refresh here, so it's only about 10 more outstanding, but depends on who accesses it.
Okay.
I think we can start. The poll will remain open, so if anybody wants to spend more time on it, that's perfectly fine.
Okay. So we'll go ahead and move to the question and then answer session. And I guess, Wouter, you and or Clark, are those in the chat, or have they been answered, or we want
They
to?
are in the Q&A. There's more just general questions.
Okay.
I've not answered them specifically, but the first one Can you also comment on the use of geosynthetics interlayers for rehab strategies?
Yeah, I kind of figured that one was going to be asked. There are some of the LTPP sites that have geosynthetics within the LTPP test sections for rehabilitation as part of the rehabilitation strategy. There's really too few to make any decision or changes to the calibration coefficients. The one thing that I will note is that the task force is considering the other NCHRP project on geosynthetics to be added or integrated into the future. So that's the reason I kind of decided not to include any comments on geosynthetics, because that might be included sometime into the future in the Pavement ME program. It's being prioritized with others this year. So, but the data that was in the LTPP database, the use of geosynthetics really didn't result in a substantial or significant increase in delay of time. So it would, agencies that use a lot of geosynthetics, or maybe a lot is the wrong word, but routinely use geosynthetics and have the data, they should use those to update and or the calibration coefficients for that specific condition. Okay, I hope that answered it.
I think so. Next, just for everyone, if you have posted questions in the chat, I ask that you please post those in the Q&A portion. If you don't see the Q&A window, it should be on, if you click on the three dots next to the chat icon at the bottom right of your WebEx window, it should show up the Q&A. It just makes it easier to follow and keep track of the questions. It's not to say we can't go to the chat, but it's just a good way to track it. So the next question, Harold, is if there's a high severity top-down cracking, how would we estimate the severity and amount if we are milling off 1 to 2 inches? I'm not sure if that's supposed to be bottom-up cracking or not. It's just
if let's say we have a pavement, and let's say flexible pavement, and let's say we have high severity transverse or fatigue cracks, either one or both, we see at the surface. We're doing our visual survey, and they're high severity transverse and or fatigue cracks. If we don't do any cores, or do no cores, then if I was a designer, then I really don't know how deep those cracks go. And if I have no deflection measurements around those cracks, then what I would assume as a designer, I would assume those cracks go through or full depth and or bottom up cracks. And so I would use include high severity cracks. And so the low transfer efficiency default would be, selected for high severity cracks. However, that's why I always suggest cores be done for rehabilitation designs. If I do cores and through those high severity cracks, and I find that those cores are confined or limited to a certain layer and or depth, like what typically can occur in segregated areas, like what typically can occur in maybe an overlay that's become debonded or has lost significant bond, and or maybe that wearing surface is starting to exhibit stripping. And I confirm that with cores that the high severity crack is limited to, let's say, 2 inches or 2.5 inches, maybe the top 2 lifts of a previous layer, then I would not necessarily assume high severity through the entire layer. I would, depending on the condition of those cracks, I might assume as a designer a low severity, and or if I'm removing all the cracks for the high severity, I would and still do not have FWD to do the back calculation, I would assume the same area and or length of transverse and fatigue cracks, but then use a low severity for those cracks if that high severity is only confined to the surface, like there's raveling going on or loss of surface material due to debonding. So that question to be answered, it depends, and it is something that a designer is going to have to decide for a specific project. I would say that there is a document that has been or is being prepared for the task force to expand some of the discussion in the MEPDG manual of practice the next time it gets edited, but balloted, but that document would have to go through the comp balloting process before it ends up in the MEPDG manual of practice. So I hope that answered the question.
Okay. Next one's kind of similar, related to the geogrids. Can the inner layer option in pavement ME be modeled as using geogrids?
The inner layer is a non-structural layer to kind of complement the geogrids and other types of materials that can be included. I'm going to remind the group, though, that that inner layer, because there were so few to be used, and that inner layer does not include the NCHRP product for geosynthetics and or geogrids that Bob Litton did. That is yet to come. But if you use the inner layer for the geogrids and other similar materials, you're not going to get a difference a significant difference. You'll get a small delay, but that's about it in transverse cracks for sure, and also bottom-up fatigue cracks. So I hope that answers that question.
Next question is, how was the 30 Hertz frequency determined? Where the elastic modulus frequency and temperature were shown, was it based on the average speed of traffic for the roadway or directly related to the FWD testing impact load frequency?
Yeah, it's directly related to the FWD, the drop loads from the FWD. The back calculation tool user guide provides the document that gives the reference for defining the 30 Hertz. That's the default value for the back calculation tool. So that's defined in the back calculation tool. There is a document on that. It's an FHWA sponsored set of research work, and that reference is reported in the BCT. I believe that reference is also included in the MEPDG manual of practice. So hopefully that answers that question.
I think so. And next question here is, in the fracture slab example, is the leveling course the same mix as the dense graded overlay?
The answer to that would be no, not in the example I used. The leveling course would be a more finer material than the wearing surface. So it was, in that example, it was simulated as a fine graded, has a higher binder content, lower air void mix. And the wearing surface has more coarser material in it. So it has a little bit lower percent asphalt by volume, and but a higher density, I believe. So they can be simulated as separate materials and separate layers.
Next question is, the simulations of fractured crack and seat, PCC, and asphalt overlay assumes 3 feet crack spacing. Do you know how sensitive that parameter is to shorter or longer crack spacing?
The crack spacing is rather limited that's allowed in pavement ME. I think the minimum is 2, if I remember correctly, and the maximum is about 5. There is a minimum and maximum limit. Obviously, the amount of transverse reflection cracks is going to be dependent upon that, because if you have a 2-foot crack spacing, crack and seat, versus a 5-foot, you're going to have a lot more, guess it's close to 2.5 amount greater from a 2-foot crack spacing to a 5-foot crack spacing relative to the cracks coming to the surface of the overlay. So it will make a difference because of the magnitude of cracks in the fractured PCC slab.
And to add on to that, Harold, too, it'll also greatly affect your IRI predictions.
It
going to have more.
can, yes, it can, through the transverse reflection cracks. Yes, it can definitely do that. The norm, or the typical, is 3 feet, and that's the reason for that. The 3 foot's the default.
And I think you can go down to 1 foot, but I'll check too.
Okay, there's a min and a max.
There is. Okay. Okay. Next one here is, can you tell us something about climate effects on these simulations, or which climate did you use? And does Pavement ME simulate effect of temperature on the load transfer efficiency?
Okay, the second part of that question, load transfer efficiency is not affected by temperature in any way in the Pavement ME. In reality, we all know it probably is, because as the cracks contract and expand, just like in a concrete pavement, you're going to lose and or gain load transfer efficiency. But it's assumed to be constant once it's measured. So it is a constant that is entered by the user or the designer, and it's not temperature dependent. The climate site, I used sites in Texas, and I used different sites. Texas was one. I used one up in the Canadian provinces to be kind of on the cold side. But the reflection cracking is less dependent on climate. It's not a relative to reflection cracking now. Climate is not a big or significant factor. Climate is a big factor, for rutting, IRI, transverse cracking, and that's new transverse cracking at the surface of a asphalt layer. So it is important, but for reflection cracking specifically, it's less important.
Sounds good. I think we have one more that came through the chat.
Okay.
For asphalt layer over CTB, how is the spacing of cracking in CTB determined if it is covered with an asphalt layer?
Oh, that's a good question. That's kind of that's a designer specific input. Some agencies have a where they will fracture prior to putting on the asphalt overlay or crack the CTB. The University of Washington, through an NCHRP project, and that is not integrated in Pavement ME, but is one of the suggested enhancements down the road. It's to use that regression equation or equation from I think it was the University of Washington. It may have been Washington State. I don't want to get the wrong university here, but they have a regression equation. That's what I suggest initially be used for predicting the crack spacing in the CTB. That is, that the user enters that value. And so depending upon that crack spacing, the amount of transverse, reflected transverse cracking is going to be proportional to the crack spacing, you know. So I generally suggest that regression equation be used, and that hopefully in the future that will be integrated in Pavement ME. So the designer could use that model if he or she desires that. But right now, that's a designer input.
Yeah, and then the attendee also updated is Washington State University.
Good. I thought it was, yeah, I said university initially, and I figured, oh, I think that was Washington State.
Okay, we don't have any current new questions. I think that's it for now.
Okay. Well, I think we're almost, aren't we, close about 5 minutes to 1 anyway?
Yep.
Central time. So with that, why don't we go, if Clark could do the closing then, and or if Ryan wants to make any final comments. I guess I would like to thank everyone for attending. And if you have any additional questions that come up, please send them to the help desk. So Clark, do you want to?
Yes, I'll go ahead and make the announcements.
Yeah.
First, I would like to thank our presenters. I thought the presentation was very helpful and very well done. So thank you. There are some announcements for this fiscal year 2022. We do have additional webinars coming up. Webinar number 2 will be on the use of innovative materials and features in PMED, and that will be on January 5th. Webinar number 3 will be an introduction to the web application. That's version 3.0 of PMED that should be coming out this summer, and we'd like to introduce that, and that webinar will be in April. Webinar number 4 will be on composite pavement design using PMED, and that will be in June. And again, I'd like to remind everyone about the user group virtual meeting that is scheduled for December 14, 15, and 16 of this year. And I'd encourage everyone to attend that. Those have been really great meetings in the past, and I think this one will be also. Alice, Ryan, is there anything you have?
Nothing I have, Clark. You covered it all.
Okay. So again, thank you for attending. You'll see some contact information and places to get additional information. For AASHTOWare Pavement ME Design, you can contact Ryan Fragapane or me. The Pavement ME Design resource website is a really useful site that all users should visit regularly. The Pavement ME Design users group contact is Jennifer Albert at FHWA. And our help desk and customer support contacts are on the right-hand side of the screen there. So take note of those and use them if you need them. And with that, we'll call the webinar concluded. Thanks to everyone again.
Thank you.
Thanks, everyone.